Now, before moving forward into deeper issues of the electric field that will help us to calculate results like these, and even in more general situations, to be able to calculate them much more conveniently, I want to point out that there's another thing that we can do as we begin to build up our database. It's this very powerful consequence, again, of the principle of superposition. So I'm going to rephrase the principle of superposition as follows. So this is going to be a principle of superposition. We previously talked about superposition for the Coulomb force. There's also a principle of superposition that goes along for the electric field. And to introduce this, let me just consider some kind of a crazy situation. Maybe one day we don't have something that is a plane or a line or a point charge, but something that's maybe a combination of these. Maybe you have some plate in your electric vehicle that is going to pick up some charge, plus sigma. And then somewhere else in the vehicle, there's going to be a line, right? A wire that picks up a charge plus lambda. And that doesn't look too neat, right? A charge plus lambda. And then maybe there's going to be a point charge that builds up on some, little bolt or something in the car somewhere else, plus Q. And now we might be tasked with figuring out what the electric field is in the vicinity of some sensitive piece of equipment. Now, rather than having to go and integrate all the charges here along the line, or all the charges on this plate, and then add in all the various point charges in the surrounding areas, which could become to be quite a lot of work and integration. And these things are all kind of complicated because they're all coming at various different angles. We would not really want to have to go back and do all of this integration. Now, if you think about it, we've kind of already done a lot of the work. We've done an integration along a line and along a plane, and we know the result for a point charge. These are all in our database. We should be able to somehow combine the results that we have to handle any situation, which is a combination of situations that we had seen previously. And in fact, mathematically, that is the case. It comes about because of the general form here for Coulomb's law. Here I'm looking at it, for the calculation of the electric field. Notice that the electric field is just a sum, right, over all of the charges in the system. And we can arrange this sum by the associative property of addition. We can rearrange the order of the terms that we sum up, right? So what we can do, for example, in this situation, is to compute the total electric field for our situation, the total, which is going to be the sum then over all charges n. And I'll write it down in terms of the trig form because it's a little less writing for me, q hat, but it's just mathematically the same statement, the unit vector direction r hat squared. But now I'm going to rearrange that sum into pieces having to do either with the line, the plane, or any point charges I have. So there'll be a sum over n that are members of the line, all the charges that belong to the line of my quantity Coulomb's constant, qn r hat n divided by rn squared. I will then have a sum over all of the charges that belong to the sheet. For my particular example, Coulomb's constant qn r hat n over rn squared. And then finally, in this case, in my example, I had just one particular point charge, so then this will be just the contribution from that charge, qn r hat n over again rn squared, where these are just n that happens to equal that particular point charge. Now, if you look at what we have here, I think you can see very quickly that this is just going to be equal to a sum of three terms. The first term is exactly what we would write down for the electric field for the line. So I'll just call this the electric field that comes from the line, plus, right here I'm just kind of separating out the two parts of my derivation, right? I have the electric field from the line. This is the electric field from the sheet. So I take the electric field from the line, I add it to the electric field from the sheet, and finally this last term that I've written is just the electric field for the point. And that then will equal the total electric field. So the principle of superposition tells us that if we want the electric field from any given situation, the total field will just be the sum of the fields from the various pieces. So if we have a database that tells us how to compute the electric field from various components in some complex distribution, we can always simply add them up to find the field for a given total situation. So our goal now is to study more in depth how we can calculate fields for specific individual situations.